In this video, I go over systems of ODEs, how to enter them into a worksheet so that non-Maple users can read them easily, and the various ways that you can present the results. Let's get started. I'm going to assume that you've seen the first two videos of the ODE sequence. So I have two first-order linked differential equations. To get the solutions, I say solutions, colon equals desolve, and then I give it the set or list of equations, P ODE and X ODE. You could put in the list of variables and some options and stuff like that, but in this case, since P and X are the only variables that depend upon time, Maple will immediately figure out that these are the variables to solve for. If we add some initial conditions, P of 0 is equal to 0, comma, X of 0 is equal to A, we can add them into our problem. Solutions, colon equals desolve, curly bracket, P ODE, X ODE, and our initial condition equations, curly brackets, and again, everything has been defined. Hit enter, and now we have specific solutions given our initial conditions. As before, we can extract out our solutions. For example, P underscore underscore sol is colon equals evaluate P of t from our solutions. And I'll put a colon there. And then, in fact, we can make a variable function out of it. P underscore underscore sol colon equals make function of P underscore underscore sol with to the right, comma, t. And now we have a function of P. Variables in Maple can be vectorized. This makes it more readable for those people who understand what a vectorized variable is. So let's create our ODEs now. ODEs, colon equals, and again, we'll start with the first order derivative with respect to time of our momentum. But now we're going to make it a vector. In fact, I'm going to put a symbol sign, Command Shift or Control Shift, double quote, put the cursor above, dash, greater than, get out of the right, parentheses t, there's our p as a function of t. That is equal to f, Command Shift, Control Shift, double quote, dash, greater than, and I'll put underscore underscore net. And this is something that's very readable to any non-Maple reader, non-Maple user. Let's add to that the derivative with respect to time of r, Command Shift dash greater than of t, which in a non-relativistic case is always equal to p of t, selecting the whole thing, divided by mass. Now, we will add in what our F net is. Let's say our force is just that of gravity, F, dash greater than, underscore underscore net, go to the right, colon equals M times G. G is also defined as a vector. What is this vector? G is, and we'll do this in 2 dimensions, has no component in the x direction and minus g in the y direction. What is r? What is p? R is a vector with respect to t, which can be defined in terms of its x value and its y value. P is also a vector with respect to t, and it too can be defined in terms of its x value and y value, which are also both vectors. Let's add some initial conditions. R, the vector at t equals 0, is going to be equivalent to 0, 0, and p at our initial time at 0 will be equal to v underscore underscore 0 times cosine of theta, and v underscore underscore 0 times sine of theta. And for those of you who recognize, this is a projectile motion type situation. Okay, we are now ready to solve solutions. : dsolve. Oops. Dsolve, open parentheses, curly bracket. There's our ODEs, comma, and our initial conditions. Close curly bracket, hit enter. And as you can see, it will go through and figure out what all the components are as a function of time. You can remake the vectors with the solutions. R is a function, so we will make a function out of it. It has something where we're going to evaluate from our solutions the vector x of t and y of t from our solutions, and we will say that it is a function of t. Now when you hit enter, it will note that this has made a rectangular table for which there are two components. The first component is this is the x solution, this is the y solution. Most of the time, I don't include that information, and it just simply leaves it as I've just made the function. Now, at any point, I can actually ask what is r at that time. R dash greater than at t underscore underscore 0 is this value. There's the x component of r, there's the y component of r. Note that it is not r of t. That does not exist. Okay, can Maple solve these sets of ODEs, which have been vectorized numerically? And the answer is yes. Just make sure that all your constants are defined, or they're defined as variable parameters. Let's triple exclamation point. Then let's solve, therefore producing a solution from our dsolve procedure, curly bracket, ICES, ODES, comma, numeric, comma, output equals list procedure, close. And as you can see, each component of both R and P are defined. You can extract out a component. For example, let's extract out y. Y solution colon equals is, we evaluate y of t from our solutions. And now if we want, we can plot y solution as a function of t, t equals 0 to 5. If you have a numerical result, then you can easily plot it. Here's a simple way to make a phase plot. We have, again, a set of ODEs where the second function is the derivative of the first function. I put some constant in, I've solved it numerically, and I have extracted out our solutions. Okay, to make a plot, that's a phase plot. We want to make a plot. We want to put our, say, theta, escape, underscore, underscore, numeric, on one axis, and our omega, underscore, underscore, numeric, of t on the other axis, and we want to use this as a parameterized plot, so we're going to plot from 0 to 4. Another way to do this is to use the DEplot procedure in the DE tools. The DEplot procedure is far more sophisticated and allows you to set up many different initial conditions. So let's set up our scenario as before, but we're going to now add in a list of initial conditions. Each condition in this list is a list itself where it has each component. There's the theta component and the omega component, and we will have two initial conditions. And now we call the DEplot procedure in the DE tools package. We give it the set of ODEs, and we describe what's going to be on the horizontal and vertical axis. There is obviously the time parameter, and here is the list of initial conditions of both theta and omega that we plan to plot. Everything else in here is an option, including what the arrows look like, what their color is, what the line colors, etc., etc. Hitting enter, you can see that the orange colors show the flow of the differential equations in this phase plot, and the green and the blue show the different types of initial conditions and how they flow. Another useful procedure for visualizing the evolution of the system of ODEs is the DEplot 3D. It is also in the DD Tools package. Pass it the same bit of information, but the third axis will be time. Everything else in here is the form of an option. Hit enter, and as you can see, as time goes by along the x-axis here, the system is curling. And if you want arrows in your DEplot 3D image, you got to explicitly include the types of arrows and the direction field. Same scenario as before. We hit enter, and now you can watch the arrows showing us the direction of the evolution of the system. The document associated with this video includes other examples and talks about how to do some animation with ODEs, or you can watch the video on doing animations and explorations using ODEs.